Hello friends, welcome to my channel. So today's topic is Euclid's division lemma. Euclid's division lemma. What is a lemma? Lemma is a theorem that is used to prove certain other statements or some results. This is related to divisibility of integers. This is related to divisibility of integers. So in this Euclid's division lemma, we will see how this can be helpful to find highest common factor, and this can also be used to prove certain other statements related to divisibility property. So let us see. Now if any positive integer a is given, any positive integer a, if divided by another positive integer divided by another positive integer b, another positive integer b, we know that it leaves a remainder. We obtain the quotient and also it leaves a remainder, and we will see what is this property of this remainder. So basically, where this division comes into account, suppose we have 17 objects and we want to distribute it among two persons. So first person equally we have to distribute. How can you do that? So obviously you can see that if there are two persons, so I have to give 8 and another 8 to the second one, and there will be remaining 1. So similarly, if you want to divide 17 objects between 3 persons, so it will be first, second and third person. So basically you will give 5 to the first person, second to the first person and third to the first person, and remaining will be 2. Similarly, if you want to distribute it among 4 persons, so we have 4 people, so first, second, third and fourth. So first person will get 4, second person will get 4, third person will get 4, fourth person will get 4, and the remaining will be 1. So what we are doing actually, so in the first case we are dividing 17 by 2, in the second case we are dividing 17 by 3, and in the third case we are dividing 17 by 4. So this is the basic division we are doing. So, and again we can also write down this 17 to be equal to 2 into 8 plus 1, and for the second case 17 will be equal to 2 into 3 into 5 plus 2, and in the third case we can write down 17 to be 4 into 4 plus 1. So what we are doing, you can see that this 8 is the quotient here. If you divide 17 by 2, you will get the quotient to be 8 and the remainder to be 1. This is the remainder. And similarly in the second case we are getting, if you divide 17 by 3, so you are getting the quotient to be 5 and the remainder to be 2. In the third case you are getting the quotient to be 4 and the remainder to be 1. So if we have A as the dividend, B as the quotient divisor, and Q as the quotient, and R as the remainder. So in that case we already know, we are familiar with this relationship from the division, that dividend is equal to the divisor into the quotient plus some remainder. Okay. Now what can you tell about this remainder? So suppose we take a division. So suppose you want 25 divided by 3. Let us do it. So 120, suppose 128. 128 divided by 2. So 3 4 are 12. 12 minus 12 is 0. Then 8. Then we go on dividing this. So 3 into 2 is 6. 6. 3 2 are 6. 2. Now we are doing the division till we reach a value of the remainder which is less than the divisor. So when we are at 8, so this 8 was greater than this divisor, so we had to again divide that. So 3 2 are 6 and we are obtaining a remainder which is less than the divisor. So one thing is clear from here is that basic principle of long division. So the remainder must be less than the divisor. And what can you more speak about the your remainder? So obviously this can sometimes be 0, like suppose 60 divided by 3. So 3 2s are 6, then 0 0, 3 zeros are 0. So in this case the remainder becomes 0 here. So your remainder can be 0 and it is never negative. Remainder is never negative. So r is greater than 0. So we can, as a whole, we can write down this r is greater than equal to 0 and r is less than b. So this implies together it can be written as, so 0 is less than r, or r is greater than equal to 0 and which is less than b. So this actually constitutes Euclid's division lemma together with this relationship. So what does the Euclid's division lemma speak? So given any two positive integers, you remember that a and b are two positive integers here. The dividend and the divisor must be positive. So if a given two positive integers a and b, so we can obtain two other positive integers q and r such that satisfy this relationship. Along with this remainder is within this 0 and b, where this can also be equal to 0. So that is the statement for Euclid's division lemma. So given two positive integers a and b, there exists unique q and r. There exists unique. Why unique? Only one pair of q and r is possible for a specific pair of a and b. If we are given two values of a and b, then there must be unique values of q and r. There are no other values possible. So there exist unique values of q and r, values of q and r, such that they satisfy a is equal to bq plus r, along with the remainder should be between 0 and r, 0 and b, 0 and b. So this is very important. So we will see that in the application part of this Euclid's division lemma. So first of all, we will see how we can find out the highest common factor using this Euclid's division lemma, and in the second one you will see that this can also be used to prove certain other statements. That's why it is known as lemma. Certain other statements related to divisibility. Statements related to divisibility property. So whenever there exists a divisibility or division process, so some statement related to some statements can be proven using this Euclid's division lemma. Also, this can be used to obtain the highest common factor. So let us first see how can we obtain the highest common factor. So what is the basic principle? So let us take one example. So suppose we want to find out the highest common factor of 15 and 18. So, so by prime factorization, we can easily obtain the highest common factor between these two numbers. So let us see. So if you factorize 15, so we can write down 3 into 5, and 18 can be written as 2 into 3 square. 2 into 9 is 18. So we can write down 2 into 3 square. So what is the common factor here? The common factor is nothing but that divides both 15 and 18, and the highest common factor. So here the highest common factor is 3. Obviously it is 3. So you can see that 3 divides 15, also 3 divides 18. But if you take 3 square, that is 9, that does not divide 15. So that is not a common factor. So we have to take a common term, and the least power we have to take. So the least power of 3 is 1 here. So the highest common factor is 3 here. So how can we find out this highest common factor using Euclid's division lemma? And why do we want to find out using Euclid's division lemma? Now the numbers are much smaller here. So when there will be larger numbers, so this Euclid's division lemma will be useful. So when there will be larger numbers, where we have to find out your highest common factor, or this algorithm. So a algorithm will be proposed based on this Euclid's division lemma, which will be known as Euclid's division algorithm. So that will be used to obtain highest common factor. So that algorithm can be used to write computer programs, so that computers easily can find out the highest common factor between numbers. So this can be implemented in computer programs. So let us see how can we find out the highest common factor. So we know that from if there are two positive integers a and b, suppose I want to find out the highest common factor between two numbers a and b. Now there must be a larger number between a and b, and we'll take a to be the larger number. A is greater than b. So can we apply the Euclid's division lemma now? If we divide a by b, so you can write down a is equal to b cube plus r. We can obtain obviously the quotient and the remainder. So you can easily express this in the form of Euclid's division lemma. So a is equal to b cube plus r, and we should note that r is greater than equal to 0 and less than the divisor. Now how to find out the highest common factor between a and b? Suppose in the first case, in the first step only, when you divide a by b, suppose r is equal to 0. Suppose if r is equal to 0, if such happens that r is equal to 0, so this a will be how much? B into q. Okay. If you do factorization of this, so this can be written as b into q if r is equal to 0. Now I want to find out the highest common factor between a and b. So let us now factorize this b. So if you factorize b, that is nothing but b into 1. So what is the common factor between this 1 and 2? So you can easily see that the highest common factor is nothing but b here. This b is the highest common factor. So that is the basic principle of this Euclid's division algorithm. So highest common factor of a and b is equal to b. When it is b, when r is equal to 0. This you should note. If the remainder is 0, and what is b? B is the divisor. If the remainder is 0, the divisor becomes the highest common factor. So this is proved here. So suppose now, so that will be our first step in the Euclid's division algorithm. So let us take another example where initially your remainder is not 0. So highest common factor of a and b we have to find out. So we know that this can be written as a is equal to bq plus r according to Euclid's division lemma. Suppose now r is not equal to 0. So what we will do? So according to the Euclid's division algorithm, so what you will do is you take the divisor to be the dividend. Now this b becomes a. Divisor will be the dividend now. In the next step, second step, will be the dividend. So that means b becomes a. b becomes a and r becomes b. r क्या हो जाएगा? b हो जाएगा. So the remainder becomes b. Remainder becomes the divisor. So rb is equal to r. Now again we can apply the Euclid's division lemma. So how do you apply the Euclid's division lemma? You take a is equal to b. So in place of a I will be writing down b, and then in place of b I will be writing down r. In place of b I will be writing down r, because now the remainder has become the divisor. So r, and if you divide b by r, if you do this division, you will get some quotient q1 and some remainder r1. So b is equal to, we can write down b is equal to r into quotient q1 plus some remainder r1. Now suppose in the second step we are reaching this remainder to be 0. Suppose if r1 is equal to 0. So what happens if r1 is equal to 0? So that means b is equal to r into q1. So now this becomes equation 3, suppose, and if you substitute this b is equal to r into q1 in equation 3, what will you get? So a is equal to, in place of b, so bq plus r, I am writing down this one. So in place of b I am writing down r into q1 into q plus r. Okay, now you should remember that we have to find out the highest common factor between a and b. So we have to factorize a and we have to factorize b. So if you factorize a now, so because initially your r was not 0, so you could not have factorized this r. Now in the second step, as your r1 becomes 0, the remainder becomes 0. Now if you substitute this b in this equation 3, as you have substituted here, so in place of b I have put r into q1. So highest common factor between a and b we have to find out. So let us factorize a. So there is a common term here, this r, so you can take that out. So r into, we can write down q1 into q plus 1, or in this form r into q1 q plus 1. Okay, now so this is the factorization of a, which is r into q1 into q plus 1. And what if you want to factorize b? So let us see. If you want to factorize b, already we have found out that b is equal to r into q1. So that is the factorization of b. So b is equal to r into q1. So what is the common factor here? What is the common factor? So the common factor is nothing but this r, and that is nothing but the highest common factor also. So the highest common factor between a and b is r. Highest common factor between a and b is r, and you should remember that what is r here. So r was the divisor in the second step. See, r was the divisor in the second step. This is the divisor in the second step. Now when the remainder has become 0, so you should remember that you go on dividing this by taking the divisor to be dividend and the remainder to be divisor. So you go on dividing this until you reach a remainder to be 0, and when you reach at a value of remainder that is 0, your divisor becomes the highest common factor. That is proven here. So now we can write down the Euclid's division algorithm. Euclid's, and we will solve some problems. Euclid's division algorithm. Euclid's division algorithm. So what is the step 1? You see in the proof. So in the step 1, what we do? So we have two numbers where we have to find out the highest common factor. So divide a by b, and obtain q and r. Obtain q and r, the quotient and the remainder. If the remainder is 0, if r is equal to 0, r is the remainder. So if r is equal to 0, then the divisor, b is the divisor here, then the divisor b is the highest common factor. Then the divisor b is the highest common factor, or it is also termed as greatest common factor. Remember, don't be confused with this. Greatest common factor or highest common factor. Now if r is equal to 0, so that is simpler. Now suppose r is not equal to 0. So we will proceed to the step 2. So in the step 2, if r is not equal to 0, we will proceed to step 2 if r is not equal to 0. So what we will do now, your divisor becomes dividend, and that means divisor becomes dividend means b becomes a is equal to b, and the remainder becomes the divisor. Remainder becomes the divisor. So that means your r becomes b. So b is equal to r. So then apply Euclid's division lemma. Apply Euclid's division lemma and divide a by b. Then proceed to step 2. Proceed to step 1, not 2. So again we will go to, so from here we will go to step 1. So what we will do in the step 1? We will divide a by b again. Now b has become a and the remainder has become the divisor. So again we can apply the Euclid's division lemma. So that is dividing a by b, we obtain q and r, quotient and remainder, and if r is equal to 0, then the divisor is the highest common factor, and if r is not equal to 0, then again we go on proceeding till we reach remainder is equal to 0. So let us take one example here. So this example will clarify our doubt. Suppose you have two numbers 15 and 18. So you take the larger number to be a, 18, and the smaller number to be 15. That is your b. b is equal to 15. Now divide a by b. So 18 by 15. So what is the quotient you get? 15 ones are 15. So your remainder is 3 here. So obviously you obtain q is equal to 1 and r is equal to 3. Now can we write down 18 is equal to 15 into, this is Euclid's division lemma, plus 3. Now if r is equal to 0, then the divisor would have been the HCF. But now remainder is not 0 here. So there is some value of the remainder. So what we will do now? We will go to step 2. So in the step 2, what we will do? The divisor becomes the dividend. Which is the divisor? So we'll go to the second step. So now a is equal to 15. That is the divisor, na? 1 is the quotient. This is the quotient. So divisor is the 15. So a is equal to 15. The divisor becomes the dividend, and the remainder. Remainder is how much? 3. So this remainder becomes the value of b. So b is equal to 3 now. Now again we divide this 15 by 3, a by b. Go to step 1. We are proceeding to again step 1. So dividing a by b. So 3 5s are 15. So we obtain a remainder to be 0. So q is equal to here 5 and the remainder to be 0. So if you write down in the form of Euclid's division lemma, so divisor is 3 into 5 plus 0. So what is the highest common factor here? So according to Euclid's division algorithm, so now as the remainder has become 0, so this divisor is now the highest common factor. Highest common factor. So now let us see another problem. This example we will take some other number, that is 135 and 225. So we have to find out the highest common factor. So first step, in first step what we will do? So we take the larger number to be a, that is 225, and the smaller number to be the divisor 135. Then we divide a by b. So 225 135 225 divided by 135. So obviously if you multiply 2 then it becomes 270. So we will go with 135. 5 minus 5 is 0. 12 minus 3 is 9, and this becomes 0. So your remainder is now, you see that from the principle of division, now your remainder is less than the divisor. Okay, so we cannot further proceed. So we obtain q to be 1 and the remainder to be 90. So what we can write down? So we can write down 225. So this is Euclid's division lemma. So divisor is 135. This into 1 plus remainder 90. So you can check in the step 1 that remainder is not 0 here. So what we will do? We will go to proceed to step 2. So in the step 2 what we will do? Now the divisor becomes the dividend a, and the remainder becomes the divisor. So b is equal to 90. Again we divide a by b. So let us divide 135 by 90. So 90 into 2 is 180. So we will go with 1. So 90. 5 minus 0 is 5. 13 minus 9 is 4. 45. So we obtain the quotient to be 1 and the remainder to be 45. Still our remainder is not 0. So we can write down 135 is equal to the divisor 90 multiplied by 1 plus 45. So remainder is not 0. So what we will do? Again we go to step 2. That means divisor will become the dividend. So a is equal to 90 and the remainder becomes the divisor. So b is equal to 45. Now divide. Then again we are going to step 1. So we are in the step 1 we divide a by b. So 90 by 45. So 45 into 2 is 90. So we get the remainder to be 0. So now quotient becomes 2 and the remainder becomes 0. So you can write down 90 is equal to 45 into 2 plus 0. So now as you have obtained the remainder to be 0, so the divisor becomes the highest common factor. So divisor is 45 here, that is b. So highest common factor is equal to 45. In the next video we will see the second application of this Euclid's division lemma. So that is basically proving certain other statements related to property of divisibility. Okay, thank you very much guys.